At this point in the course, you are already familiar with some of the simple gas laws, such as Boyle's law, which states that pressure and volume are inversely proportional. Charles's law states that volume and temperature are directly proportional. And for all of these gas laws, we are assuming that the moles of gas are held constant. You're not adding or removing any gas from one change to the next. And then finally, we add Gay-Lussac's law, which reminded us that pressure and temperature are directly related. If you were to plot each of these laws real quickly, you would see that pressure and volume are inversely related, and the graph looks like this. Charles's law shows us that volume and temperature are directly related, and the graph will look similar for Gay-Lussac's law for pressure and temperature. And again, for all of these, the amount of gas is held constant. And remember, the variable of the three that you see that is missing from that particular law is the one that is held constant. For example, Boyle's law, we don't see pressure, we don't see temperature. So that would be constant temperature or isothermal. For Charles's law, we don't see pressure, so that would be constant pressure or isobaric. And for Gay-Lussac's law, we don't see volume because volume is a constant. So you could call that isometric or isochoric. In some situations, neither pressure, volume, nor temperature are held constant, though for the combined gas law we will still assume that the moles of gas is held constant. So when neither pressure, volume, nor temperature are constant, then you have to show all three variables. The combined gas law is P1 times V1 divided by T1 equals P2 times V2 divided by T2. As you can see, the combined gas law is the other three gas laws combined into one equation, where Boyle's law can be seen here, Charles's law can be seen here, and Gay-Lussac's law can be seen here. Because no one variable is held constant with the exception of moles of gas, you will see all three variables. The combined gas law can be used in place of any of the three basic gas laws even if something is held constant, because that variable, which is held constant in this case, of course, will cancel out. So if you're doing a problem where it mentions temperature and the temperature does not change because the temperature is constant, what will end up happening is that the temperature will just cancel out on both the left and the right, leaving you with Boyle's law in the first place. Rearranging the ideal, or the combined gas law I should say, is simply algebra. If we're tasked with solving for the final volume given other information, we need to solve for this V on the right, which lets me know that you need to get rid of all of the variables on the right that are not V. One simple trick is to move things to the opposite side, both of the equal sign and of the fraction bar. So P2 needs to get away from the V2, which means that it would go in the denominator on the left. T2 needs to go away also, which means that it will go in the numerator. Since it's on the denominator on the right, it'll go in the numerator on the left. If I were to rewrite this, solved for V2, I would get T2 times P1 times V1 all over P2 times T1 equals V2. And at this point, it's simply plug and chug. Now, in a different situation, we might have to solve for the initial temperature. If you look at the left side, I have some variables I want to get rid of. I should get the P1 and the V1 to the other side. To do that, I will multiply both sides by the inverse of P1, which is the same as dividing both sides by P1, putting P1 in the denominator on the right. The same thing will happen to V1. Multiplying both sides by the inverse of V1, or dividing both sides by V1, we'll put V1 on the bottom on the right. Now I'm going to rewrite it to clean it up just a little bit. One of the most common mistakes students make when they rearrange things algebraically is forgetting to flip everything if they need to. When you're solving for a denominator, such as solving for either T1 or T2, you will get 1 over the temperature when you move the pressures and the volumes to the opposite side. Remembering that everything should be in Kelvin, forgetting to flip everything will give you a temperature that doesn't make sense. It'll give you a very tiny temperature because you're solving for the inverse. For example, if you were doing this problem and you got a number that was very tiny, something that did not seem reasonable, you may have solved for the inverse of the Kelvin temperature. After flipping or inverting the entire equation, you will then solve for the normal temperature in Kelvin, and everything will cancel out in its place. After having solved for the initial temperature, you have your final answer in Kelvin. If the question asks for the temperature in Celsius, remember to work with Kelvin mathematically and then convert back to Celsius if necessary.